Kind of. See if I can make my laptop here. Not bad. No, laptop is mine. There. See if I can remember my password.
Difference, should she give you back partial credit, or you more satisfied with your grade now?
Oh yeah, I got it. I got plus 11 points. 11.
That's a lot.
That's a lot.
Yeah.
You don't go never be late again.
Okay. Is that really the 27th o'clock?
We had a lengthy discussion about automation and running it. It didn't go well.
So, right now, you should be.
I like automation.
We're done.
Automation is kind of good because we get all kinds of crap really cheap. You go to places and buy stuff that isn't very good, but it's very cheap.
Let's not start that argument. Let's just learn about the history of it.
Okay.
I really think we should reignite.
We should do what?
We should reignite our thing.
Reignite the automation or handmade argument. I'm a maker. You know what a maker movement?
Yeah.
There's this place in downtown New Haven called Make Haven, and you can go there and do tools. It's so much fun. I really believe in making stuff. It's good for your soul.
Like giant cathedrals.
Yeah, for instance. Okay, I am sorting through this because I have a surprise for you.
Is it cookies? Is it cookies?
I
Cookies?
could have
Is
brought
it an
cookies.
egg?
I didn't bring cookies.
Why did you wear cookies?
Wilfred.
Oh, it's all.
Next time we brought fried chicken to linear algebra. That was a good
It's not cookies.
You don't want it. It's not cookies.
What if it's an egg?
So
Cookies. Cookies are better than that.
I actually graded papers up until I got to Kevin, Michael, and Masao. So you guys are not going to get your papers back unless you can do it while everybody else is doing a group activity. So that may happen. But,
Okay.
you know, before the end of the day, maybe. Yeah, maybe, right? Erica?
Still look at this question, we didn't get to the end of it.
Robert. Kayla?
Like he's just waiting for me for my one piece of being
Not today.
To be fair, in Word it was one page long. And then with the references that you can page.
In Word, mine was one and a
Word
half
is
pages,
thinner stuff.
in LaTeX it was
It really
less
is.
than a page.
That's weird.
Giovanna Mancini. There we go.
What was the
Can't do it
format
with-
setting? Like, what's the setup? Sorry,
Shit.
report. Yeah,
Oh, by the way, the
Like
numbers
the-
up
whatever
in the
the
upper right
thing
corner
it
are your
automatically
grade
makes
out of
it.
20.
Make the print much smaller.
Chris.
Nobody gives me an A minus.
I figured out how to make it bigger.
No, well, you get to
50.
revise and get to its
It's
ones.
not coming here. It's just literally taking back to large.
Oh, Vicky.
Or taking a capital L and it's bigger. Which I do log capitals, and it gets bigger. I type huge minutes.
What has happened to the screen? It's gone dead.
The screensaver turned on.
Why would they do that? Why would they do that?
Because if the screensaver will work, we will save the screens.
Okay. So, you know, you don't need another reminder about paper number 3, do you?
But we have a third paper.
What is this?
Friday.
This is.
You might want a reminder about this. I didn't ever, this isn't a reminder, this is a first announcement of it, but we're going to have our second quiz Friday. Covering the homework that we talked about last time, which was 3.2 and 3.3. And I want to mention a couple of things about LaTeX to help you with these last papers and formatting in particular. One thing is, I think by default, the font is like 8 points or something, it's ridiculously tiny, so you can, at the very top of your document, it says slash document class and then article. You insert square braces right between the document class and the curly brace article. Square braces that say 12 points in them, it'll make a 12-point font. If you think that's too big, make it 11 point, that's fine. But for my eyes, please make it 12 point, actually, for my, do 12 point, I like large. So that's one issue. The other thing is for papers that I got to write comments on, you need to leave me a little room for it. And LaTeX doesn't do that automatically, but there is a variable called line spread, which will separate the lines, so it'll spread things out, the spacing a little bit. You can use line spread 1.5 or as much as 2. I wouldn't go beyond 2. 2 is full, really double spacing. So we were talking about constructability of various things and things that can't be constructed. Remember that last time? The more modern approach to this is to think about numbers. And say a number can be constructed or not constructed. And what is constructible numbers? Basically, plus, minus, times, and division. Right? Do the 4 operations. Plus, you're also allowed to do square roots. So if you can make a thing using those 4 operations, then you've got constructible. Can pi be created by using plus, minus, times, divides, and square roots? Not likely. Maybe if you go to infinitely long things. But yeah, no. So pi is not constructible, but you know, like square root of 17 is. And then there is a theoretical result, which I'm not going to get into too much, but this is what Gauss used to show that the 17 gon and the 65,537 gon could be constructed. If you've got a constructible number that's equal to 1/n of a full circle, the cosine of that number, cosine of that angle is a constructible number, then you can construct the pentagon. So yeah, there's a nice connection between the numbers that you can achieve by using operations and square roots, and the figures you can achieve by ruler and let's say ruler. Straight edge. Okay, so then we're almost done with you, but there's one last thing I want to tell you about. Probably single most important algorithm in number theory and in computer science these days is his antideuresis method. I said that wrong. Antideuresis. Does that sound better? Anyway. You don't have to worry about how to pronounce it now. It's the Euclidean algorithm. It's a standard algorithm, hugely important in like internet commerce. You know how there's these when you go to like a site that you're going to put your credit card number in, you get that little lock symbol in your browser that says you're secure. That security relies on the Euclidean algorithm. Believe it or not.
Is it like an encryption algorithm?
Yeah, so the most standard encryption that people use for public transactions like that is called RSA.
Yes.
Revist, Shamir, and Abelman. And one of the important things you have to do in RSA is to find the multiplicative inverse of a number that's part of your key, modulo some gigantic number. Well, the way that's done is using the Euclidean algorithm. What the Euclidean algorithm actually does is find the GCD. And that, yeah, it determines the GCD of 2 numbers. So do you know what the GCD is?
Greatest common divisor.
Greatest common divisors. Is it also greatest common factor?
That's just,
Well, true, but aren't they the same?
Yeah.
There's just two different ways.
Divide.
But then there's another thing that's the least common multiple. You know how those are related?
GCD, A and B times LCM of A and B equals A and B.
That's right.
We're taking abstract, so.
Oh, you are? Okay, good. So you should probably know the Euclidean algorithm, and let's do it. I think I want to do it.
Please know it's just.
No, wait. Let me first explain why it works. It's a classic example of a canonical kind of algorithm called recursion. So what a recursion does is looks at a problem and goes, I can reduce this one to a little bit easier. Now, look at that problem. Right? There's It's as if you just hop over and go, okay, now I've got a new problem, it's easier. I look at that one, oh, I can reduce this one to another problem, it's easier. Hop over here and do it, right? So, the point is that if you've got a pair of numbers A and B, and say A is the smaller one, their GCD is the same thing as A and R, where R is what you get when you find the remainder that you get by dividing A and B. So that's a theoretical fact. You could actually sit down and prove that. It's not too hard to do. But for us, just notice what it does. You're starting with A and B, now you've got A and R. And R is smaller than the divisor, right? So R is definitely a smaller number than A was. So now A and B have become R and A. I set them in the right order for a reason. A is now the bigger number and R is the smaller number. R is taking the role that A formerly had. Okay. So let's do an example and you'll see that this is pretty easy. I didn't actually do this out ahead of time, so let's see how it goes. My A and my B are 273 and 168. So a very standard way to show that you know what's going on with an algorithm is to do what I'm about to do, which is make a table and kind of list the values of all the variables at the different stages through the algorithm. This is almost a single line for each stage, so we don't have to make too big of a table here. Just worry about it. Can you see that? So I want to have A and B, and notice how I need to find out what the remainder is. I'm going to do this by actually writing the whole little expression we get for doing division. It's B is equal to quotient times A plus the remainder. We're going to really focus on the plus R that's on the end of that. But still, that's the expression. So we start with A, the smaller one is 168, and the bigger one is 273. So then I write 273 is, how many times does 168 go into 273? Can you see that up here? It's in once, right? 1 times 168 plus a remainder, that's just the difference. Can't do it in my head. 2 and
105?
73, 105?
105.
Is it 105? Okay. So now I get to use this factoid that the remainder and A have the same GCD as the original A and B did. So I'm just going to put 105 here where the smaller number was, and 168 where the bigger number was. So look what it looks like happening. It looks like the 168 just slides down into that position, and the 105 you see on the end comes back in. Close the screen again. Using my laptop wasn't the smartest thing. Yeah, I got to figure out how to turn that off. Remember next time to download the slides onto the Blackboard note. All right, so what's the division algorithm say here? We get 168 is something times 105. Oh, that goes in once too.
Yeah.
Right? So it's 1 times 105, and the remainder is 63.
Yes.
So what are the new A and B the next time through this process?
63 and 105.
Yes, in that order, right? And 105 is equal to 1 times 63. You might start to guess that I cooked up this problem.
Well, you said you didn't check ahead of time.
Oh, I know, but I still cooked it up. You see what the quotients are always turning out to be 1? There's a reason for that. When the quotients, when you go down the line, the quotients all turn out to be 1. You've got the maximum runtime for the algorithm. So I wanted you to see that a lot of examples for it. Usually the algorithm runs really fast. Like, you can have 200-digit numbers and get their GCD in 6-7 iterations. You know, fast, like microsecond fast. Anyway, what's the remainder going to be here? 37 and 5. 42? Okay. So the new numbers are 63 is there and 42 is there. And we go 63 is 1 times 42, and what's that remainder? 21. So the new numbers are 21 and 42. Ooh. Let's see there.
2.
21 and 42. It doesn't go in once anymore.
Is it twice?
42 is 2 times 21. And then 0 is the remainder, and that's our stopping criteria. By the way, I should have probably said that up front, right? You want to know when does it end? Because at some point, and any algorithm ought to come to a stop and tell you the answer. This is that point. That's our, when we get 0 right there, that's how we know to stop. So what is the actual GCD? It's the last remainder we got, right there. Or you can see it as it's now A. So if you go through the other process, I think I'm going to go through the other process, and then you can tell me which you think is faster. Do you know what I mean by the other process for finding GCD?
Like the tree method?
Yeah, factor. Find out what the prime factors of those numbers are, and then just pull up all the common factors that they have, all the primes that they have in common. So how hard is it to factor these guys? You start with 168, 168, not 5. And you notice it's even, right? So you pull off a factor of 2, and what remains behind is 84. Oh, even again. Another 2 comes out, and you get 42. Well, even again, 2, and you get 1. And that's 3 times 7. So collecting all this up, it tells me that 168 is 2 cubed times 3 times 7. There's the factorization. Now, what's the other number?
273.
73. I'm not spotting the evenness there. Is it divisible by 3?
Yes.
Oh, it is, because what is it? That adds up to 10, and 2 more is 12. 12 is divisible by 3, so this is, you know that trick? You add up the digits, what was that? Add up the digits, check whether they're divisible by 3, or that sum is. So this is equal to 3 times something. Not as
91.
bad mentally as you might think, because 3 goes into 27 9 times, and then there's, that's 91. 91 is one of my favorite primes.
Why so?
Well,
Why so?
because it's divisible by, it's divisible by 7, because it's not a prime. It's the one that fools people every time, though. Right? I mean, you look at it and you go, well, it's not even, it's not divisible by 3, that must be a prime. But it's the first one that is not divisible by any of the really small numbers. So, and there's no nice rule for figuring out something divisible by 7. Well, there actually is a rule, but it's not a nice rule. And so, yeah, this fools people all the time. It's not, in fact, a prime. I just said 7 goes into it. Right?
It's the greatest common.
Can you see what the other factor is? 13. So, what do these guys have in common in terms of their prime factorization? This is 3 times 7 times 13, and that's 8 times 3 times 7. Primes they have in common are all the same. So, what we got here, 21. It worked, right? But which is better?
Well, for small numbers.
This.
Yeah.
Oh, this is better. For any number that you can do by hand, factor. Right? Now think about it, what it looks like when the number has 200 digits in it.
Well, nice.
And it's not even, so you're screwed right off from the back. Suppose you've got an odd. In fact, in this encryption scheme we were talking about, RSA, what the number you're dealing with is the product of 2 prime numbers that are similar size, several hundred digits. So you're not going to find any small factors, ever. I mean, the sun will have burned out by the time you find the first small factor in it. Factoring it is utterly impossible. Okay, I just said that, and there's actually a little revolution going on in computers right now where they're trying to develop University rely on quantum mechanical principles for their operation. And it is thought that quantum computers will break this RSA system. That they're going to be capable of doing the operations fast enough to be able to break RSA and get your credit card number from Amazon.
I'm glad we're
Watch out for that. And also watch out for Experian.
Bottom line, use Amazon Cash.
Well, you know, the real trick is to move into Bitcoin. If you start using, you know, one of these cryptocurrencies, there's nothing to steal. It's just data that's going across the world. All right, so I mentioned that we could just factor, but not when they're big. Okay. This is the new guy we want to talk about. The only image that I can find of Eratosthenes. He's got a skull rather like my own, sort of wow. And with those spots on it too. He was born in a place that's now Libya, which is one country over from Egypt on the top half of Africa.
No, it's a neighboring state.
Their neighbor, yeah. So this was close to Egypt, close to Alexandria, where the center of scientific life happened at that day. He studied at Cyrene. Somebody here was doing Zeno as their Greek philosopher. He studied under Zeno or Zeno's own student. I'm not sure which it was. But yeah, it's like either the child or grandchild intellectually of Zeno. And then he went to Athens and studied there under the leading lights of the day in Athens. And think about what this says. The big cheese in Alexandria, the king of Alexandria, Ptolemy III, called this guy from Athens and brought him there to be a tutor for his son, for the royal prince. What does that say about a guy that somebody from 800 miles away who's got the ability calls on you and says, I want you over here to be the tutor for my son? He's like 25. Right? And he had become so famous amongst the Athenians for his mathematical ability that his word spread. And now, I don't think we've talked about the Ptolemies yet, so I should mention something about the context here to the story. You remember Alexander the Great? We talked about him, and I think in the that comes in a second. I think in the history of the world video, they had they showed this. Alexander the Great had conquered pretty much everything that was civilized, and then he died, and his stuff got all split up amongst his generals. So Ptolemy was one of the generals. That's Ptolemy the First. This guy set up a dynasty, and it was a dynasty that was based on intellect as much as military might. They certainly had military might. They were bad. They also set up this museum in Alexandria, a city named after Alexander the Great. And in the museum, there's this library that was the biggest thing in the world in terms of a library at the time. So after tutoring the king's son for a little while, the librarian died. And he's only in his mid-30s, he becomes the librarian. Now this is like being the head of the National Science Foundation thing. He's like considered the top scientist / mathematician / philosopher / ethicist in the world. There's some funny shit in here about his nickname stuff. You've heard of a pentathlon. So to call him Pentathlos was kind of a compliment. It was saying, this guy is good in a whole bunch of different events. But the book makes kind of a deal about the calling him Beta, which was not a compliment.
Oh yeah, beta. Isn't beta like less dominant males?
Well, that's what they now talk about in wolf packs. You've got your alpha male, and then there's betas. Everybody else who's not alpha is the beta. But to these guys, beta was just the second number. It was number 2. I mean, alpha was our alphabet comes from alpha and beta and gamma, etc. So that word should tell you that alpha is their first letter and beta is their second. And we know that they used letters for their numbers, so beta is just number 2. What they were really saying is, you're number 2 in everything.
second only to the king.
No, not the king. They were talking about intellectual pursuits. So the king was smart, but he wasn't like one of the luminaries. But he's the number 2 number theorist in the world at that time. He's the number 2 geometer in the world at that time. He's the number 2 astronomer in the world at that
Wait,
time.
so you're losing to all the same people or to different people?
Oh yeah, all the number 1 people are different people. There's nobody who's number 1 in 2 things.
So
Okay,
he's
so that's
number
good.
1 in the jack of all trades deal.
That's my thought. You know, I'm not sure that was an insult. I think that might have been what they call an underhanded compliment. Calling you number 2 is, this sounds, really, it sounds bad now that I say number 2 out loud. You've had children, you'll understand. So, but saying that you're the second best guy in every scientific discipline in the world, that's a compliment, not an insult. In any case, they probably didn't call him beta to his face. I don't know whether this is true or not. It's a myth, who knows? But the story is that he lost his vision when he got to advanced years. He lived to a ripe old age. And no longer being able to read was such a big deal to him that he committed suicide by refusing.
They didn't have Braille.
No, it's the preferred way to go if you're an older person. A lot of older people just stop eating in their homes. And they,
But this is more depression than like contemplating suicide.
once you get past about day 3 or 4, you stop being hungry.
Yeah.
And all you want to do is lay around and fall asleep one day and you don't have a wake up. But I don't know whether that's pretty. I mean, how many of us would do that and say, "Oh, I can't read books anymore. I'm out of here."
We got Braille.
I would say I would be tempted, but I think I could be like, "Isn't there one of those audible things?"
Yeah.
You didn't have it.
Yeah,
You probably had
it said, call the person next to you, read this for me.
You can picture somebody reading it for him. He didn't. So remember the Delian problem? I don't know how to say it. Delian or Delian? The duplicating of the cube. This is where we needed to construct a cube whose side was cube root of 2 times the side of the original cube, and then that'll stop the plague that's wiping out Galvus, was, and hence the name Delian. He was able to solve this, and what he did was create a mechanism that solves it. I guess I should show you the mechanism. I can't really. I wanted to build. I told you I was a maker. I wanted to actually make one of these, but it was kind of a full night last night, so I didn't. But it's not too bad to imagine. So I'm going to just try to show you a picture. Glasses. Okay, so after that, Eratosthenes right here. Here's the. Let's zoom it in. The thing at the top of the screen is the mechanism, although it may not be obvious that it's a mechanism. But the rectangle AFGR has a diagonal drawn across it. That would have been a piece of brass that was engraved with that diagonal line across it, and it was rigged to slide along these lines. And the next rectangle, you can't see all of it because part of it is underneath the other one. It would go R prime to wherever here is to H to S. That's another copy of that same brass rectangle. It's slid so underneath of the first one. And then the next rectangle ends at TI, and that's slid under that one as well. So we've got these 3 overlapping rectangles. Now, there's a line that goes straight down here that crosses the edge of the 3rd rectangle there at D. And see how that line, that segment is marked as A? And this segment is marked as twice A? That's what we're doing. We're trying to find the cube root of 2. So this mechanism is going to locate the cube root of 2 by a weird little trick. What you do is slide the rectangles around until the line intersects V at the point that's A units up here, and then slide these other guys around until the diagonals cross that line. Just laid out. So that you might do this line from A to E with a piece of string or something across the face of the thing. And then start sliding these rectangles until everything lines up the way it does right now. So you understand that this is not a geometric construction, it's moving the mechanical pieces around until they move places. But there's all kinds of similar triangles on the page right now. Once you put those sliding glass plates in the position that's shown here, let's see how many different similar triangles we have. Well, D to I to E is similar to C to H to E, is similar to B to G to E, and A to F to E, right? There's a whole ton of similar triangles. Look at these ratios, they said are all equal to each other. I think I want to do the last, this first one last. Here's H. Oh, HE is this, okay, is to GE, okay. What HE to GE should be BE, this one, to AE, holy shit, it's up here. Because there's another set of triangles I didn't point out to you. Let me show you the other set of triangles. They're using these diagonal lines that go across the plate. So EIC, it kind of has a oblique, what is that called? An obtuse angle at the eye. And then EHB, that's similar to the first one, and so is EGA. So this equality is using similarity in one of those triangles that has an obtuse angle on it. But this last equality is using the upright 90-degree triangles. So I'm pretty sure that's right. B to E is the same as A to E, or in proportion to A to E as F. G to E is F to E. So you see that we've got similarities there? We've got some more of these things. B to G is, BG is to AF as GE is, I'm going to ask you to sit down and try to work your way through all of those things and verify that all the equalities of ratios that are shown there are true. Let's cut to the chase. If you take the particular line segments that are given here, called first DI is A, AF is twice A, and then you've got unknown things, X and Y for these other guys, you get this equation. If A is to X is to Y, is Y is to twice A. This is called a pair of mean proportionals. So that X and Y sit in between A and 2A in such a way that you multiply by, think about it as multiply A by X and then multiply that by Y to get to twice A.
Okay.
Well, X, it turns out, is the cube root. Wow. Because think about what the cube root of 2 does. If you multiply by the cube root of 2, that gets you to X. Multiplied by the cube root of 2 again, that gets you to Y. Multiplied by the cube root of 2 a third time, that's 3 copies of the cube root of 2. So you multiply by 2, that gets you to twice A. This weird, ingenious design allows you to construct a number, not construct in the usual sense, but to find a number that's cube root of 2 times the size of the original number. So Eratosthenes, who came up with this while he's at the museum, he's working for Ptolemy III, thought this was the biggest deal he had ever seen. It solved the Delian problem with the mechanism. So he had a beautiful version of the mechanism built, and they put it up on a pedestal, and it has this poem to the king about how this was dedicated to the king. I'm thinking the king wouldn't have been that excited about this. So it shows how Eratosthenes thought. Okay, back to regular stream. So that whole thing about having a mechanism, that's not the rules that we're supposed to use. The construction with straight edge and compass, so that's what it still was pretty ingenious. Let me talk about some other things this guy did. Way, way before Christopher Columbus, he knew the Earth was a sphere. He knew the Earth was round, and he was able to figure out how big of a sphere. Accurate. I mean, really, really accurately to like 2 decimal places. And the things that he had to measure in terms of were something called stadia. You know how long the football field is?
100 yards.
100 yards, plus there's like 20 on each end, so 140 yards. Then there's about another 100 yards on each end for stands. That's a stadium. A stadia was the length of the arena that would hold sporting events. And that's roughly the same size we use today for soccer games or football. Okay? But you can imagine, there wasn't just one stadium. Right? There were different stadia all over the place. Different cities had different sizes. So this was just a really crude measure. Hey, it's about, it's probably somebody, you go about 3 football fields from there and you'll see the turn. It's not terribly accurate. And how would you actually, if you were in the ancient Hellenistic Egyptian world, how would you measure football fields? Probably going, let me just count to 300 as I walk, right? Just pacing it off. So, and that's what they did. They paced off the distance between Alexandria, which is at about 30 degrees latitude, to a city called Cyrene. No. Just said the wrong thing. Cyrene's where the guy was born. Syene, without the R in it, it starts with an S, is this other city in Egypt, a little farther south. And so it's on the same line of longitude as Alexandria, but it's down along the Nile. It happens to be on the tropic.
Capricorn?
Is it Capricorn? or
Cancer?
Cancer?
Cancer.
I can never remember which is which. The northern tropic,
Yes.
anyway.
Cancer.
Right?
Capricorn.
So what's the, do you folks know the significance of the tropics? These particular lines of latitude are about 23 degrees.
It's where the sun goes, like at the height of summer, like the sun goes all the way up to the whatever the northern tropic is, and then for the equinox, it's more towards the equator.
For the equinox, it's right at the
Yeah,
equator.
the equinox is at the equator. Then for winter, it's at the end of
Southern.
summer.
So that's the point. At Syene, on the summer solstice, the sun was dead straight up. So they could prove this. If you had a well at Syene that went straight down into the ground, on the summer solstice at noon, light shone completely down into the well. You can see the bottom. They lined up. And then at Alexandria, if you had a well, that wouldn't work because you're about 6-7 degrees farther north. So your well would, the sunlight would come in on the side of all the well. So I believe what they did is built a tower for this. And they measured the angle that the shadow of the tower made. So they've got the distance from Syene to Alexandria, and then the angle that's created by this tower. Let me take a little picture. Okay, this will be the equator. Here's the, whichever tropic that is. I want to say it's Capricorn.
But Capricorn, I think it's sun.
Anyway, that's the point that is the sun is directly overhead. Here's the sun. I'm drawing it much smaller than our aliens. Right, so at Syene, a pole would have no shadow right at noon on the summer solstice. But at Alexandria, it would. So the pole would stick straight up out of the earth, and the light from the sun coming in here would make a slight angle. So he was able to measure this angle for you. Now, actually, I made it look like a nice angle, but the sun is really far away, right? It's 93 million miles from us. And this distance on the sphere isn't really very big. I think it's 6 degrees of latitude, so they're fairly close together. There's a couple of 100,000 stadia, remember that. But it's a geometry problem now, right? You know how much of an angle there is between these two guys because of the and you know what the circumference of that piece is. So now you can figure out the circumference of the sphere. Cool. I would like to challenge you to try that. Just take the numbers in it and see if you can figure out the circumference of the sphere. What's amazing is that it was close. It came out to within about 1,000 miles of the real number to the other day.
Only the Earth is a sphere.
Well, it's awfully close to a sphere. It deviates from a sphere by a few percent.
But is that few percent would cause something to be off by that much?
Oh no. In fact, the deviation in form hardly affects the circumference to diameter ratio. All right. Going blank again. So that was a pretty amazing computation, but he did other things like that. He figured out how far away is the moon. I mean, I'm not sure I could do that now. Really?
I'm sure you could if you put your mind to it.
Well, I mean, he did have a lot of resources. He had an unlimited number of slaves. I mean, he could say, all right, I need you guys to carry that telescope way over there, and somebody would do it. But, the sun, the moon, those things he all figured out. What I want to end with is the Sieve of Eratosthenes. I'm sad that I'm ending with this, because there's so much to say about Eratosthenes. How about this guy? It's cool. Everybody know how to find prime numbers?
Yes.
How do you do it?
If you give us a seed, it's the numbers over here.
Table.
If you give us the thing, isn't it the numbers in that table?
Yes, I'm giving you the first, all the primes up to 5,000 on one sheet of paper. Isn't that exciting? You have to figure out how to read this table. Darlene, have you seen this already? I've shown you. No? I don't know why I'm taking this so slowly. Pass it around.
There's a problem here. 91 isn't on here.
Better not be.
What?
Have you figured out how to read it already, Michael?
Yeah.
So the rows represent hundreds, the columns represent the tens.
You can see the H and the T and the headings, hundreds and tens.
Yeah.
Can I get everybody now? So this table, let's see if we can just do a quick example on it. The point of the table is you've got T's, which is the tens placed across the top, and H's, the hundreds placed on the top, down the sides. And then all it does is in a particular block, it gives you the final digits. So if we're in about 31 hundreds, and 10, 20, 31, 31, 31, odd number. That's what it's telling us. And then, because there's no 3 in that position, 31, 33 is not. 31, 35, well, okay, nothing down here is going to be 5, is it? Can you find the 1, 5 in the table? There it is. Yes, there's a 5 up there. It's just right near the top. So every prime ends in 1, 3, 7, or 9. That's kind of an interesting little factor. All right, so how did the sieve work? This is silly to try to do this now with 2 minutes remaining. Let's just say this. Are there any even numbers?
2.
And that's it.
Yeah, 2, and that's it. So the first step of the sieve is circle 2, so I found a prime, but it's the only prime that's divisible by 2, so I cross off every other even number. That is, I think about starting with a shape like this, where you've got all the numbers written down up to some point. Everything even can be knocked out, except for the 2. So our very first stage would be circle 2, and then you can actually just cross out whole columns worth of stuff. Because all the even numbers line up. And I've done the numbers from 1 to 10 across each row, and then 11 to 20. So all the even numbers, these guys are all even because they end at 0. These all what's the next prime after 2? You know this.
3.
All right. So 3 is a prime, I'll circle it. And now I need to knock off everything that's a multiple of 3. So 6 is gone, 9 is gone, 12 is gone, and that 6 was already gone. 12 is already gone. 15 is the new one that's gone. As I'm knocking off the multiples of 3, half of them have already been erased. That's okay. We're not worried about overkill here. In fact, overkill is kind of nice. So some numbers will have been crossed out half a dozen times. They've got a lot of factors, and they'll be crossed out multiple times. What we're interested in is the ones that end up not being crossed out. So the ones we're crossing out are called sieved, and the unsieved things that remain behind are the primes. Not quite as simple as that. You'll know they're prime so long as they're not too big. You'll still have uncrossed out stuff down the road that's not prime, but it's because of some number you haven't gotten around to sieving out.
Would you say that prime numbers are uncivilized?
Never apologize for a really bad one. Never. Just say it again. Okay, so we'll do this in class on Friday.